This is the first seminar of a cycle of 4 seminars. The first one is entitled Allan Variance and Friends, and I will mostly talk about Allan Variance, which is the archetype of all the variances, but you have to know that there are many, many other variances. And I will explain what is the use of the variances in the time and frequency metrology. The other seminars would be devoted to first in March on variance uncertainties, and I will explain what is a Bayesian approach in order to compute the uncertainties of the variance measurement. So it's the link is directly linked to what I will say today. The third one will be devoted to cross spectra in France, to retrieve the same style of title. When I say the same style, I mean that I will deal also with the covariance, which is something which is very cool, which is like the sorry, I don't remember the name, the tricorner hat. Perhaps you already heard about the tricorner hat. So it's a derivative of the tricorner hat which uses covariances. And the last one will be devoted to holdover and long-time extrapolation. What happens if you know very well a clock during, let's say, 1 day or 1 hour, and you want to extrapolate what will be the behavior of the clock after this time? So it will be in May. Okay, so today's special will be first an introduction in order to have in mind something that I think you already know, which are the basic quantities in time and frequency. The second part will be devoted to the Allan variance itself. And after that, we will explore some different variances. And lastly, I will detail what is the practical use of the Allan variance and how it is possible to get information from Allan variances. So introduction, first I will remind what are the notation in the time domain, what are the notation in time in the frequency domain, and what is the noise model, which is directly linked to the notation in the measurement and the notation in the frequency domain. So everybody knows that if you have an ideal oscillator, if you could have an ideal oscillator, of course it doesn't exist, it's in the world of the ideas, in the Platonician world, you just have to know 3 parameters. The first one is the amplitude, which is the intensity of this sign. The second one is the frequency, or its inverse, which is the period. And the third one is the phase, phi. And if you know those 3 parameters, you know what will happen to this oscillator from the beginning of the universe to the end of the universe. Of course, it's not possible. Such an oscillator doesn't exist, so you have to deal with a real oscillator. So there are many ways to modelize a real oscillator. In this case, I will only consider what happens with phase. I will transform this parameter in something which is vary with time, which could be random, which could be deterministic, but in our case, it will be mostly random. And we will see that it's also linked to the frequency noise, but it's enough to have something which is variable here. I will not speak about the amplitude noise, which is another problem. I think Enrico will be more efficient than me for explaining that. So phi of t, in this case, is so-called phase noise, is something which is mostly random, but it's expressed in radian, but generally people prefer to use another quantity, which is x of t, which is called the time error or phase time. And it's exactly the same thing, except that we have divided by 2 pi and the nominal frequency of the oscillators. In doing that, it's possible to put that in factor with 2 pi nu 0, so you have a quantity which is also a time, which is expressed in second. And this is the quantity that you use if you say, for instance, my watch is 39 seconds late, because it means that if you look to your clock and to a reference clock, which is represented here by a cesium clock, you see that there are 39 seconds difference. You have the time given by your watch and the time given by the reference. You make the difference between them, and you obtain minus 39 seconds. This is clearly what is the so-called time error, the x of t, that I will refer explicitly several times in this talk. I told you that it's possible to go from the phase noise to the frequency noise. If you have a sine, the argument of the sine, we can deduce from the argument of the sine, which is here, you can deduce easily what is an instantaneous frequency, because it's a time derivative of this quantity divided by 2 pi. So if I do that, I will obtain a first part, which is the time derivative of 2 pi nu 0 t divided by 2p, exactly nu 0. You retrieve the nominal frequency of the oscillator. That's quite normal. And the other part is the time derivative of the phase divided by 2 pi, which is, in fact, the frequency noise, and which could be expressed in Hertz. But generally, in time and frequency, we prefer to use another quantity, which is not directly the frequency noise, but which is the so-called frequency error. And you divide the frequency noise, which is here, by the nominal frequency of the oscillator. It is something like the percentage of the variation of the frequency compared to the nominal frequency of the oscillator. So the advantage of this quantity is the fact that it's dimensionless, so you can compare the frequency deviation of a clock running at 10 megahertz and a clock running 10 gigahertz, for instance. You directly have an idea of the stability of each of these clocks. So the main quantities that we will have to use are x of t for phase and y of t for frequency deviation. These two quantities are two representations of the same phenomenon. You see that, in fact, you have directly a link between y and x, because y of t, the frequency deviation, is nothing but the time derivative of the phase time of the x of t. But there is a fundamental difference between them. The first thing is the fact that if you deal with phase, or x of t, because x of t, it's a phase with a coefficient, it's possible to get them instantaneously. You can directly know what is the phase at an oscillator at one time, a very accurate time. But it's not possible to know the instantaneous frequency instantaneously. You are obliged to make an average. For instance, in this representation, which is only an ideal representation because it's not possible to know exactly what is y of t instantaneously, as I said. But imagine that the blue curve here represents y of t, and you know it very precisely a long time. The only thing you can know is the average of this quantity during an interval, a time interval, which is tau in this scheme. And of course, you can have tau, which could be very small. You could have tau, which is 1 microsecond, but generally it's more or less 1 second, because with variance we deal generally with more or less long-term stability and not short-term stability, which is generally in the frequency domain. So if you want to measure exactly what is the frequency in this interval, the average frequency, you can integrate that from tk, which is the time which is here, to tk plus tau, which is the time which is here, and you divide by the width of the interval by tau. So you have directly the average during this interval, but thanks to the fact that y of t is the derivative of phase time, you can directly use this relationship. You measure the phase time here, tk plus tau, minus the phase time here, tk, and you divide by tau, and you will directly have the frequency deviation, what is interesting generally in order to use the Allan variance. How is it possible to get that? It's possible to get that, for instance, with a time interval counter. A time interval counter is a device on which you put the output of your oscillator to the start, and you put the reference oscillator to the stop, and the counter will be launched when there will be the first rising edge. I put here a square signal, but it could be a sine signal. It doesn't matter. The counter will be launched when you have the first rising edge, which is here, and it will stop when there will be the first rising edge of the reference. And in this case, you are directly at the measurement of the time difference between these two rising edges, so directly a measurement of x of t. There are also many other measurements. We can measure directly frequency with a frequency counter, a reciprocal frequency counter, phase meter, and so on. I will not detail. It's not the topic of my talk. It's also possible to make a frequency down conversion. For instance, you can go from microwave to RF with bit nodes. You can also use a frequency comp if you want to go from optical domain to RF and so on. What is important also is that nowadays it's possible to have a device which makes many samples per second, typically, for instance, 50 megasamples per second. So if you are interested in something which will last about 1 second, you can divide it into many sub-samples, tau zero here, and imagine that you have 50 million tau zero in this interval. You can have the classical rectangular shape, which is given by the pi counter, but it's also possible to have now, with the lambda counter, a shape which is triangular. You see all the steps, but if there are 50 million steps, it seems to be continuous, of course. And it's also possible to have omega counter, and here we have a shape which is parabolic. What is the advantage of doing that is the fact that doing that, particularly the omega counter, which has been invented by Enrico here, you have the best rejection of the white phase noise. And why is it interesting to reject the white phase noise? It's because generally the white phase noise is due not to the device under test, but is due to the measurement instrument. So if you remove it, you are able to see what is really the noise of the oscillators that you are measuring, and not the noise of the measuring device. This is the variance, which is 1.5 lower than the variance of the omega counter. Why does it change? Ah, yes, okay, it changed. Now let's go to the frequency domain. You know that if we want to deal with the frequency domain, we will have to make a Fourier transform. The classical Fourier transform is given by this relationship. But this is something which is correct for finite energy. And you know that mathematicians say that it's possible only if you have a function which is in L square, something like that. Do you agree in the back? In physics, generally, we don't care. Perhaps we are wrong, but generally we don't care. But we have to be conscious that if you have a signal which have a finite energy, I mean, if you have imagine a quartz oscillator, if the quartz oscillator runs from the beginning of the universe up to the end of the universe, the finite will be the energy will be finite, but very large. And the more you wait, more the energy will be important. So it's not a it's really a problem. So generally, what we use is something which is signal of power finite energy, and if we use finite energy, in order to give the spectral density, you should only to have the square of the modulus of the Fourier transform, which is here. But if you deal with power spectral density, you have to take into account the fact that the power is finite, but not the energy. So you have to transform a little bit the Fourier transform algorithm. You limit to a time interval t and not to infinity. So you go from t minus 2 minus t over 2 to plus t over 2, and you have to divide by 1 over t, and of course, you are theoretically obliged to have a mathematical expectation of all that. You can imagine that it's an ensemble average. Imagine that you have an infinity of clocks which are exactly the same, but completely independent, completely uncorrelated from the statistical point of view. It's a little bit crazy, but we have to imagine that, and you do the average of all that. This will be the power spectral density. Perhaps I have to add, yes, t should tend toward infinity. So it's really a mathematical expectation. It doesn't exist directly, but you have to estimate, you have to find an estimator of that. And what is the estimator is the first one I presented to you. This is an estimator. It's called the periodogram, which is an estimator of the power spectral density. But we will see later on what is the difference between this estimator and the real power spectral density. So we have to recall also, to remind also some result of signal processing. If we have a function of t which is multiplied by constant a, you know that in the frequency domain you have to multiply the Fourier transform also by the constant a, because it's a linear process. And if you deal with the power spectral density, you have to multiply it by a square, and you have a modulus because a can be complex. And if you make a time derivative here, you can, if you make a Fourier transform, you have to multiply by g to p f. So it will be, f is the Fourier the Fourier frequency, and if you deal with the power spectral density, it will be 4 pi square f square s phi. And you will see that it's very important, because if we deal with time error, there is just a coefficient between phase and time error. So you just have to take the square of this coefficient because it's real, and you have the spectral density of x, knowing the frequency density of phi. The dimension here, you have t to the square divided by t, so you have the dimension of that is the time. It's expressed in seconds, but generally people prefer to express that in Hertz minus 1. So in this case, you have this, which is expressed in Hertz minus 1, divided by Hertz to the square, so it's expressed in Hertz minus 3. If we deal with the power spectral density of frequency deviation, which is very used, and I will mainly focus my topic on this quantity in the spectral domain, you will see that you have a time derivative here, so you have to multiply the spectral density of time error here by 4 pi square f square. So you have to multiply by f to the square, which increases with the frequency. So it will change the behavior in the frequency domain. The coefficient is a little bit different here if you deal with the phase power spectral density. So in this case, the dimension is Hertz minus 1. And this is very important because we generally define the noise model in the frequency domain, and the power, it's generally considered that it's enough to have a power law model with 5 different power laws, with alpha going from -2 to +2. You have here the Fourier frequency, which is f, and you have this different type of noise. The most well-known noise is, of course, a white frequency noise, which is a constant, whatever the frequency, the Fourier frequency is. But there is also some other noises. And for instance, you see that since the relationships that we saw just previously, you see that the link between spectral density of phase and the spectral density of frequency deviation is f square divided by nu zero square. You see that if you have a white noise, in this case, it means that you will, with the frequency, it means that the power spectral density will be in f square. So in this case, you have, it's this case here, you have f minus 2 for the frequency. No, it's not. Yes, if this is white, you will have a spectral density of frequency which will be in f square. That's it. You have a white phase noise here, and you have f square there. But you can also have a white frequency noise, and it depends on the oscillator, because an oscillator is generally considered that we have a resonator, an amplificator, and depending on the scale where this noise will appear, it will be integrated or not. If you have a white noise and this white noise is integrated, you will retrieve so-called random walk. So it's possible to explain all these different type of noise by this sort of things. But there is also another very mysterious noise, which is the 1 over f, the flicker, and we can retrieve the flicker integrated or directly. So this is flicker FM or the flicker phase modulation. And this is also something which is very important, which is present everywhere in many, many different domains of physics, in astrophysics and so on. Just to have an idea of what are the differences between these noises, I plotted two different noises. The first one is a white frequency noise, and this is expressed in the frequency deviation. So you see that in this case, in the time domain is the left part, and the right-hand side part, it's frequency. So we have a classical Gaussian noise. It means that the only information you have about this noise is the fact that it's centered here around 0, and it follows a Gaussian shape. Imagine that the probability is maximal around 0 and very low when you increase the value here. And the only thing you know that this is this sort of probability. But you can know all the history of the noise. You don't have any further information about the position of the next measurement. It's completely uncorrelated. There is no correlation between each of these quantities. It means, in other words, that the instability of this clock is the same if you are looking at very short term, because the next sample could be here, as is the same if you are looking to the long term, because the sample which is here can be very far also from the previous one. I say vertically, of course. And this can be observed in the frequency domain. If I make the Fourier transform of that and I take the square of the modulus, you have the so-called periodogram, which are the different red dots which are here. You see that it's still very random, because the Fourier transform of a white noise is itself a white noise, but here you have to take the square of the modulus of the noise, so it's positive, and its average is no longer 0. But you can compare it to the power spectral density, which is the blue line. And imagine that you make the average of an infinite number of oscillators which are exactly with the same type of noise, the same amplitude, but completely decorrelated. You will finish by obtaining this straight line, which is here, which is continuous. Anyway, what is very important is the fact that you have the same amplitude for low frequencies. Low frequency, it means long term. And for high frequencies, it means for short term. So it means that you have the same correlations, it's the same dispersion between short-term samples and long-term samples. It's completely different if we look to the random walk. I remind that the random walk is the integration of a white noise. If you look at the random walk, you see that the next, for instance, you can consider this sample, which is here, right here. You see that the next sample will be very close to this one. It's completely improbable that the next sample should be here or there. But if you are looking far here, you see that the probability to have a sample which is very far from this one is relatively important, very low, for instance, in this case. So it means that you have a very small amplitude for short-term variation, a long amplitude for long-term variation. And it's what is visible on this curve in the frequency domain. You see that here also you have the periodogram, which is the red dots, and the power spectral density, which is the blue line. You see that there is still a random behavior, but it's not so strong as previously. You really see the behavior in 1 over f squared. And what we can see that for low frequency, we have a huge amplitude, so it means for long term, and you have a small amplitude for high frequency, so for short term. So it's two possibilities to explain what we observe in the time domain or in the frequency domain. So let's go to the Allan variance. First, the definition of the Allan variance comes from the definition of the true variance. The true variance, you know what is the true variance. There is a mathematical expectation here also, but imagine that if you have an infinite sequence, imagine that the blue curve here infinite from minus infinity to plus infinity, what we have to do is to measure its average and to remove the average of all the data. In this case, it's not very important because it seems to be more or less centered. And you take the square, and you have one value for the length of this data. If you have a true sequence with an infinite number of samples, n in this case, you just have to make the estimation of it. It's not really the variance, but you have to estimate it. And you will consider that we will transform the mathematical expectation of the value here by an arithmetic mean. You make the difference between each sample and the arithmetic mean. You take the square and you make the average of all that. You have to divide by n minus 1, but it's a detail which is not important here. The problem when you do that is the fact that you have only one sample. You have only one sample, which is for tau equal to the duration of all the sequence. It's not possible to know if it's a little bit more stable for short term, long term, and so on. This is the first problem. The second problem is the fact that if you have low frequency noises, I mean flicker frequency noise, and random walk, it will not converge. So in this, for instance, if you have a random walk, the longer the sequence, the higher the variance. So by definition, it doesn't converge. If you have an infinite sequence, we will have an infinite variance. So it's not possible to use this sort of estimator in time and frequency because random walk is something which is very frequent, as well as flicker and so on. So we have to find another estimator, and it has been done by Dave Allan in 1966. He got the idea to transform this variance over n samples by a two-sample variance. And in this case, he transformed this sequence by looking only at the two first samples. And he makes directly, if you detail what happens here, you will obtain y2 minus y1. So you do y2 minus y1, you take the square. And after that, y3 minus y2, and you take the square, and so on. So it's something which is very interesting because you will have convergence, and I will prove that it's true later on. We have convergence, and it's possible after that to group all the samples 2 by 2, or 3 by 3, 4 by 4, and so on, in order to have the variance. If you take the first two ones minus the third and the fourth other samples, and so on, you can extend the duration of your variance. You can go up to the half of the sequence. The last samples you can obtain for the longer term is to take the first half of this sequence minus the second half of the sequence. You take the square, and you have only one sample. You are not able to make an average, but it's useful for that. But what is important in this case is the fact that you are still something which is an ensemble average, but could be also a time average, because in many cases we consider that we have ergodicity. It means that we have the same statistics if we deal with ensemble average. You remember what is ensemble average? It means that you have an infinite number of clocks which are identical, and with time average, and you are looking to your clock at one time, the day after, the 1 year later, and so on, and you make the average of all that. There is also something which I have to keep in mind, is the fact that if I do y2 minus y1, I take the square and I move this pattern all along this sequence, I'm doing a convolution product. And this is very interesting to think that what is a convolution product in time domain? It will give a filter in the frequency domain. So this is very important. What is the pattern of this convolution? I call it hi of tk of t is only this figure here. You have remember minus y1 plus y2, you take the square and you move it. So you have at each time a convolution product, you take the square and you make the average. So if you go back to the frequency domain, it means that you will have exactly, it's possible to show that you have directly an expression of the Allan variance in the frequency domain, and you have here the power spectral density, and here you have a transfer function, which is nothing but the Fourier transform of the pattern, which is here, this pattern. And it's very easy to calculate the Fourier transform of this pattern. You don't need to have Mathematica or something else. It's possible to do that directly, and you have this response, which is very important, this transfer function. You see that you have a sine 4 of an argument divided by the argument to the square. So it means that if you have an argument which is small for low frequencies, you have a behavior which will increase like f squared. This will be important for the following of my talk. So if we look for convergence of the Allan variance, we can see that there will be a convergence for some drift because it's a first order difference. A first order difference, it means that it's more or less a derivative. So it will be that it means that it will not be sensitive to constant. If you have a constant, if your sequence is constant, you will add and subtract it. It will be 0 everywhere. But on the other hand, it will be sensitive to linear frequency drift. If we are looking in the frequency domain, imagine that we have random frequency noise, which has a spectral density in blue here in 1 over f squared. If you multiply it with the transfer function, which I presented you in the previous slide, you see that you have here something which increases like f squared, here something which decreases like f minus 2. So it will converge. And if you make the product of these two curves, the blue one and the red one, you have the green one, which is here. And you see that its integral is finite. The integral is the zone which is in pale green here. So it will converge. It's a big advantage relatively to the classical Allan variance. The classical variance, sorry. Unfortunately, it doesn't converge for F1 and F2 because you remember that you have something which is divided, a sign which is divided by f squared here. If you multiply it by f squared, it will have the response which is given in green. And if you are going for frequency to infinity, it will not converge. So you are obliged to introduce a high cutoff frequency in order to have convergence of the Allan variance. And the Allan variance, the result of the Allan variance will depend on this high cutoff frequency. Yes, this will be the problem. This slide is probably the most important slide of my talk. So if you have to remind something, try to remind what has been given here. I remind here what is the expression of the Allan variance. If you look it in the Fourier domain, you have here the spectral density, and you have here the response, the transfer function of the Allan variance, and you can compute this integral by changing all the different type of noise. I mean by changing alpha here from alpha equal minus 2 to alpha equal plus 2. And in this case, this time you can use Mathematica because it's a little bit more difficult. If you put here h minus 2, f minus 2, you will obtain as a result of this integral this quantity, which is proportional to tau. If you replace it by h minus 1, f minus 1, you have something which is constant, the response is constant, and you retrieve here the noise level. And what is interesting for you, if you are dealing with the estimation of the stability, is directly to have the measurement of all these noise levels, h minus 2, h minus 1, and so on. You will completely define what is the noise of the oscillator. And if you look at the Allan variance curve, and the advantage I already told you is the fact that you can change the tau parameter, you can make tau equals the sampling period, 2 times the sampling period, 4 times the sampling period, and so on, you get a very smooth curve. And a very smooth curve is very easy to fit, and you can try to determine all these different asymptotes which are here, tau, constant, 1 over tau, 1 over tau square, for these 2 ones. You see that, as I told you, it depends on the high cutoff frequency also. It's a problem of Allan variance. And in this case, you can see that here you have something in 1 over tau square, so it's generated by this noise. Here you have 1 over f. Just something, here you have ADEV. It means Allan deviation is the square root of the Allan variance. Generally, people always plot ADEV and not Allan variance, but you have to go back to, you imagine that you have the square of that. So here you have 1 over f, it's 1 over tau, sorry. Here you have a constant, and the constant gives directly, the value of the constant gives directly here the noise level which is there. So it's very useful in order to retrieve what are the noise levels of the signal of coming from your oscillator. So you have directly measurement of the noise. So you directly have a spectral analysis of of the noise of your clock. It's also valuable for determining the linear frequency drift, because if you have a linear frequency drift, you will have also a slope which will be in tau square. Okay, so this means that you can retrieve almost the same thing if you are dealing with the spectral density or with the Allan variance. Is it really true? First of all, there is a main difference. If you look at this power spectral density, which is the same that the one which has given us the EVAR which is there, it seems to be the same, but you have to remember that the first difference is the fact that you have here high frequency, so low frequency, sorry. Low frequency, it means long term, so it should be linked to this part, and here you have high frequency, it means short term. So first of all, you should have to flip the picture like that. Now we have here, I will translate this into frequency. Okay, so now we have low frequency here, a higher frequency here. Okay. Secondly, you remember that you have, if we have something which is an asymptote which is constant here, it means that you have 1 over f. 1 over f, it should decrease. So you have to turn the picture. I will turn the picture. Okay, and now you have something which is quite the same, that is 1. Very interesting, you see that there is a very huge error bar here, and you know that there are very few estimates there. It's not, obviously, it's a consequence of that. Okay, so it's possible to retrieve more or less the same information with Allan variance in the classical power spectral density. Nevertheless, if we have, for instance, a very sharp spectral line, imagine that you have a spectral line which is just here. You look at the response of the Allan variance with, you see that there is this little thing which changes there. The asymptote which is here has a little bit changed, but it's not very sensitive. It doesn't see directly this. If you have a big sign like that, now you have a bump which is here. So it's possible to detect it. You see that something got wrong. You don't know exactly what, but what you have to remember, if you have very fine details in the spectral density, you better be using the power spectral density than the Allan variance. Allan variance is a little bit short-sighted. It can only give you the large trends of the spectrum, but not the fine details. So if you want to go to the large trends, I mean the tendency of the flicker on the 1 over f and so on, you have to use the Allan variance. But if you can also use, of course, a power spectral density. But if you want to see the fine details, you have to use the power spectral density. last but not least, sorry, how is it possible to compute the Allan variance if you have some, you choose, in this case, we choose to have tau equal 3 times the sampling period. The sampling period is the small step which are in blue here, and the pattern of the Allan variance is this one, which is 3 times. So we are interested in this case in the stability of your clock for time interval of 3 times the sampling period. So the first possibility is the so-called Allan variance with overlapping, and you move at each time. You see that I have moved from 1 tau 0, 2 tau 0, and so on. And I will move that over the whole sequence. The other possibility is to do that without overlapping. I mean that I will directly move the pattern in red by 3 tau 0. Toc, 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 toc. What is the best way? There are advantages and drawbacks in both cases. The benefits is, of course, if you do the first way, you will have 3 times, in this case, 3 times more value in order to make your average, so it will be lower dispersed. But in the other case, you will have an higher dispersion, of course. But doing that, you have more correlated estimates because at each time you will use 3 times the samples. But it's not really a severe drawback because generally the samples are itself correlated, because if you have 1 over f or a random walk, they are correlated. So it's not really a drawback to use correlated estimates. We will have to take that into account later on when we will discuss about uncertainties, but for the computation, it's not a problem. Sometimes when I want to explain really what is the computing of Allan variance, I use a spreadsheet. It will not be possible here but when I make, during EFTS in class lab, I give to people a list of value. Here you have something which figure out what are the time, here the frequency deviation, and it's possible to directly calculate the Allan variance. And you, for instance, here, I will just describe what happens here. For instance, this value here is the average of B4, B5, B4, B5, it says 2 ones, minus the average of B2, B3. You take the square and you divide by 2. And after that, you make the same, but you change by 1 step at each time. So it's directly the average of all that, which will give you the response of the Allan variance for 2 tau 0. And this is the Allan variance, this is the Allan deviation, and you see that if we, no, it's not possible to see it. So if you do that, I see, yes, you see that it's exactly the same result that you obtain if you use the code ADEV, which is a part of sigma theta. I will deal with the different solutions which is possible to use in order to compute the Allan variance. Okay, so it's something which is very basic. It's not at all difficult to understand what happened with Allan variance. It's possible to do that with the more simple spreadsheets. It's possible to use numeric, for instance, but you can also use another spreadsheet. But spreadsheet is not really efficient to make Allan deviation or Allan variance. You better be using sigma theta. I will explain what is sigma theta later on. So there are Allan variance and Allan deviation. What is the best to use if you want to consider the stability of your oscillator? If you consider the physical meaning, it's much better to use Allan deviation because you can interpret it directly as a time uncertainty about a time interval. For instance, you have tau, which is equal to 1 day. For instance, you could take a cesium clock. You know that in 1 day you have a sigma, an Allan deviation, which is 10 to the minus 14. It means that you have 10 to the minus 14, which is equal to the time uncertainty divided by the time interval, which is 1 day. So it means that you have approximately 10 to the minus 9, it means 1 nanosecond per day. So a cesium clock, typically, it's 1 nanosecond per day. So it directly, you directly have the physical meaning. The same way, if you consider the frequency, you can also consider that it's a frequency uncertainty divided by the nominal frequency of your clocks. For instance, if you have a need measure which works at 100 megahertz, if during tau equal 1 hour you have 10 to the minus 14, it means that the excursion in frequency of your hydrogen measure is approximately 10 to the minus 14 multiplied by the nominal frequency 10 to the 8. It means 10 to the minus 6, 1 microhertz per hour, which is also classical for an hydrogen measure. So it's easier to use, and generally people prefer to use Allan deviation. But we have to remember that there is a severe drawback. It's easy to interpret, but if you want to fit, for instance, the curve like I show you in the previous slide, I don't remember where is this slide. Yes, like that. If you want to find the asymptotes, you have to remember that the square root of the sum is not the sum of the square root. So you have to deal only with Allan variance, because if you try to fit the Allan deviation, you will get a mistake. Okay, never fit the Allan deviation curves, always the Allan variance. Very, very shortly, because I'm running late a little bit. How is it possible to estimate the uncertainties? I will just give you a few clues today, and it will be the topic of the next session. So you remember that the estimate is given by this quantity. So you have each value which are considered to be Gaussian and centered. So it means that if you take the square of them, it will be a chi-square distribution, a so-called chi-square distribution. I will explain that later. And if you have the sum of n chi-square distribution, chi-square distributed variables, random variable, you have theoretically a chi-square distribution with n degrees of freedom. But this is true only if the samples are uncorrelated, and it's not at all the case. So you have, in order to compute really the uncertainties, you have to measure what is the correlation between the samples. This is a major issue, and after that there are algorithms which give you directly what are the error bars. But how to estimate the equivalent degrees of freedom, please go to the next seminar, it will be explained. So what you have to remember right now is the fact that if you make Allan variance, you have generally a curve like that. In this case, it decreases, so it seems to be a wide frequency noise. But generally, you see that the error bars increase with tau increase. And generally also, and it's very important, and I know that Enrico is very careful about that, the error bars are longer upward than downward. Be careful for the PhD student. If you present a seminar, if you invert the error bars, Enrico will be severe. Okay, other variances. You remember that Allan variance is a variance which is first derivative. Here we have the Hadamard variance, which is sometimes also called Pissambono. Oh, I see that I make a mistake. It's 1 over 6 and not over 9 here. Okay, because there are some problem of normalization of this variance, but yeah. Okay, something is in progress also to correct that. Okay, what is important with the Hadamard variance is the fact that we have a second order difference. It means that with the second order difference, you are insensitive to drift. So it's possible if when you have a clock which drifts, generally the fact to use Allan variance means that we will have an asymptote which will increase very, very quickly. So it hides what is behind. If you use the Hadamard variance, you will have a variance which is not sensitive to drift, so you will only see what are the long-term fluctuations and not the drift. So it's very useful for that. Another variance which is also useful is the modified Allan variance, because you remember that one of the drawbacks of the Allan variance is the fact that it doesn't distinguish F1 noise and F2 noise, I mean flicker phase noise, the white phase noise, and it doesn't converge for these two noise. If you replace here the square that we have previously by a triangle, you see that you have a triangle shape, and this is directly linked with what I told you at the beginning of my talk about the different counters that you can have. There is a pi counter, the lambda counters. If you use the lambda counters, you directly can obtain the modified Allan variance, and it's very useful because you will have the possibility to distinguish F1 and F2 noises, and we don't need anymore high cutoff frequency. And there is a time variance, which is basically the same, but which is multiplied by tau square. If you take the square root of that, if you take the time deviation, you directly have a result in seconds. So it will tell you that the instability of your clock for 1 hour will be something expressed in seconds. And last but not least, the invention also of Enrico, which is the parabolic variance, which uses the omega counter. The advantage of this one, it's not very used, but we hope that it will change. It's recommended with omega counters, of course, but it will allow us to have the best rejections of the white phase noise. I will not detail this curve, but what is very interesting to see is the fact that we no longer have the same, for Hadamard, you have the same value, the same response here in tau minus 2, and you see that there is a high cutoff frequency, and you no longer have a high cutoff frequency with modified Allan variance with the parabolic variance. And you see that we have 1 over tau square here and 1 over 2, 3 there, so it distinguishes directly this different type of noise. What is very important to notice also is the fact that wavelet analysis, the Allan variance is very close to wavelet analysis. And if you look to one of the well-known wavelet, the R wavelet, is directly the Allan variance. You directly have the same. So in our opinion, Enrico and mine, we think that it's a pity that people in time and frequency are not close enough to the community of wavelets, because it's a very large community, much larger than the community of time and frequency, and they have done many mathematical and software developments which could be very useful for us. And unfortunately, we don't benefit of all that. Quickly, it will be to present my third seminar. How is it possible to get the stability of one clock? It's not possible to get the stability of one clock if you have only one clock. You need at least a reference clock. And if you take a reference clock, theoretically, the reference clock should be much better than the clocks that you are measuring. So you take, for instance, a clock like mine, and you take a cesium. I think the cesium could be, the instability of the cesium could be neglected regarding the one of the watch. But if you have two clocks, which are about the same stability, you can imagine that if you make the Allan variance, you will have half of the variance which will be due, half of the instability which is due to clock 1, and half of the instability which is due to clock 2. Okay, perhaps it's true, but it's never possible to go further. You can know if there is one which is a little bit better or not. In order to go further, you have to take at least 3 clocks, and it is the so-called 3-corner hat. You measure the clock A versus clock B versus clock C, and clock C versus clock A, and sometimes it's possible to derive from that the stability of clock A, B, and C, and it's the so-called 3-corner hat and Groslambert covariance, but this will be the topic of the third seminar, so I don't go further at this point. And I will just finish, if it's possible. It's possible, Samuel? 5 minutes. You can go back. You can go out. Salut, Jack. So first of all, imagine that you have this sort of measurement. You have measured the YK samples of one clock against another one, which is a better one, and you calculate the Allan variance, and you have that. What can we do with that? First of all, you have to see if there is an asymptote. The first one, obviously, is this one, and it seems that there is another one which is horizontal, so you fit, and you obtain this sort of fit, which is quite good. So you see that there is here an asymptote with a level which is about, I see more than about 4 10 to the minus 28, and 1 over tau asymptote here, which is 6.5 10 to the minus 23 at 1 second. So tau minus 1 constant. You have to go back to what I presented to you in another slide. You see the responses of the Allan variance for all this type of noise. You see that here you have the response which is in 1 over tau, and it is due to the wide frequency noise. And here a constant, a response which is constant, and it is due to the flicker 1 over f. So we have directly these two noises, which are identified in your sequence. So in order to go further, you have to remember that, I go back to this response, the white noise is the asymptote of the white noise is 0 over 2 tau. And you know that the asymptote of this white noise, we have measured it just before, is 6.5 10 to the minus 23 2 minus 1. So it is equal to H0 over 2 tau. So you simplify by 2 here, and you multiply by 2 there. So you have 1.3 10 to the minus 22 seconds. This is the white frequency noise level. If you do the same with the other asymptote, which is flat, you have 4 10 to the minus 28, which is equal to the response of the Allan variance for the flicker, which is 2 log of 2h minus 1. You just have to divide that by 2 log of 2, and you obtain the value of the 1 over f. So you have directly a model of the spectral density, which is here. You have a spectral density which can be modeled by a constant part and a 1 over f part. If you are interested in the time domain, in the time stability of your clock, you can consider that you have the Allan deviation. Now you take the square root. If the time is very short, you can consider that this term will be dominating, and this one can be negligible. And in its case, for tau below 1 day, you have an Allan variance which is equal to that, 8 10 to the minus 12 tau minus 1/2. This is the behavior of this clock. And if you have time which are larger than 1 day, you remove this one and you take just the square root of that, you 2 10 to the minus 14. So you know that this is the so-called flicker floor of the Allan deviation. For instance, this is approximately what you could obtain with a cesium clock. So it will be very interesting to fit that. But remember, as I said, the fit should be done not on ADEF, but Allan variance only. If you want to fit, you can imagine that you have 5 here different asymptotes from 0 to 4, which are directly a power law of tau. And you can use the classical least squares. The classical least squares, you take the absolute difference between each measurement and the curve. And you have to minimize the square of this difference. Of course, it's not, you have here a log-log plot. If you have here a log-log plot, it means that you have here something which is at least 100 times smaller than what happened here. So if you have constant, if you are looking at constant difference, very small difference you see should be very large there. So you have to take into account not the absolute difference, but the relative difference. And this is done here. You have to normalize, to weight this difference by the value of each data. You have that divided by this here. And you have also to take into account the error bars which are there. And the error bars, the length is more or less proportional to the equivalent degrees of freedom. So if you put the equivalent degrees of freedom as a weight, another weight, you have a double weight in this case. You have something which is really suitable for fitting the variance curves. This is what is used in my in the sigma theta and this sort of codes. So you have to find all this fits, so all this coefficient, and after that you can also consider the uncertainty of the noise level. I don't dare to show you, but it was a paper from mine in 1993. Déjà. Well, what happens if you want to extrapolate? For instance, you have a curve which is, you know very well the behavior of your clock up to, in this case, it's, let's say, 2 days. After 2 days, what happens? Perhaps you can extrapolate this curve. But you have to be sure that you have the longest term asymptote which has been defined. And you should be sure also that this asymptote has been well determined. It means that you have, it is dominating at almost 1 octave, perhaps 1 decade it would be better. And you have to look also if a null parameter is compatible or not. If a null compatible is compatible, you can consider that you don't have a good determination of your curve, so don't try to extrapolate. If you answered yes to the question 1 and 2 and no to the last question, you may try. And this is what we do. This is the well-known problem of holdover. You know very well the clock in this interval, and you want to know if the fit that you have performed will be good by extrapolating. So we introduced a new quantity, which is the time interval error, which is the difference between the fit you did here and the behavior of the clock, the real behavior of the clock. And it's possible to estimate the variance of this time interval error. And the maximum time interval error can be computed. But this will be, this is what you will discover in the 4th seminar, is what is written. So, to finish my talk, and I'm sorry to be a little bit late, what software exists for frequency stability estimation? In my knowledge, there are 3 of them. The first one, which has very used for a long time, which was Stable 32, unfortunately is no longer maintained, so I'm not sure that it's still possible to do that. The other problem is it's only a graphical interface. It's a proprietary code also, and it's very difficult to do something a little bit which is not the thing which has been imaginated by the author of this code. There are 2 other possibilities. One is more or less for Unix and Mac OS, which is sigma theta, which has been done here by several people who are here, like Jean-Michel, Benoit. This code is it's the opposite. It's a command line interface, so you have different commands, and you can chain the command with a script, for instance. But they are open source, and you can do what you want with that. And you have something which is a little bit intermediate, which is written for Python, which is called Allan tools. And there are many Python functions which work very well, but it's a little bit long because you know that Python is interpreted and not compiled. So now what is the new thing is that we are trying to make a bridge between sigma theta and Allan tools. It means that we are trying to make a command line of sigma theta, which is possible to code them with Python. So Jean-Michel and Benoit are the master of this bridge. I think that's all, and I thank you for your attention. Yes, the variance for other quantities at time. There is something which is very important in what I showed previously, is the fact that
you should have samples which are integrated without dead time. In my opinion, it's very important to keep this in mind. It's not possible to use Allan variance in the same way that we use it in the time and frequency domain if we have instantaneous value with a long dead time between them. So if you take care of that, for instance, you can use it with temperature and know that it's sometimes used with temperature. We tried to use it in geophysics with some colleagues a few years ago, and it could be interesting, in my opinion, to use it for other quantities. After that, you have to have an idea of what could be the noise in the quantity that you are using. Is it sensitive to white noise? If it's only white noise, perhaps it's not necessary to use Allan variance, but if there is flickers, if there is some other noises, it could be interesting to identify them. So the response is yes, first, if you have data which are sampled without dead times, first, integrated and sampled without dead times, and if you are interested in see different signature in frequency, different type of noises.